Hi everyone, I'm teacher Ellie.
And my name is Teacher Miguel. Today we have the pleasure to start our data structure class. It is important for you to learn about data structures as your careers focus on creating complex softwares.
For this purpose, we are providing you a paper that we are going to share, so let's get started. Okay, I'm seeing good answer, but no, what is an efficient algorithm? An efficient algorithm is one that can handle various types, size of data quickly and accurately using the less possible time or time complexity and the smallest amount of resource such as memory or space complexity.
But also we talk about an effective algorithm. An effective algorithm is the one that can produce the correct result for any valid input. It focuses on solving the problem accurately no matter how much time or resource it takes. I will give you an example. So you have a bookshelf with totally basic books. You don't like the disorder and like the books are organized there. So you decide to order by colors how you want. Then, even if it takes time, the result will be always correct.
Now, let's talk about the importance of data structures. Data structures are essential for computing because they provide a way to organize, store, and retrieve data efficiently. Without them, programs will have to rely on simple sequential arrays, which will be impractical for many real-world applications. For example, a tree data structure can store information in a hierarchical way like a family tree or an organizational chart. They also make complex algorithms possible like quicksort and merge sort, which rely on arrays and binary trees to sort large data sets efficiently.
Answering these questions, I will give you an example to understand why data structure is important for modern computing. Imagine your spine. Without it, you won't be able to perform many of the tasks you do every day. Well, data structure is the backbone of computing. They provide the lead to organize, store, and retrieve data. Without them, we will be limited to simple sequential arrays, which are slow and impractical for virtually any real-world application. Imagine trying to manage a massive database with millions of records using only a single array. It will be a logistical nightmare, leading to slow queries and also costly errors.
Let's look at table 1 in the paper. It showed something called time complexity and space complexity. So what is annotation 1 in time complexity? It means constant time. The operation always takes the same amount of time no matter the size of the data and for example, accessing an element in an array by its index.
Now, I know that some of you have been asking me about the old notation, the time complexity column in the table. So that means that the execution time of the algorithm grows proportionally to the number of elements contained in the data structure. So I will give you an example. You're searching for a specific book in a messy pile. You have hundreds of books and you look for it until you find it. So the time it takes increase proportionally to the number of books.
And what is O annotation in space complexity? It means linear space. The amount of memory needed increases proportionally to the number of elements. And, for example, a linked list with n nodes occupies space proportional to n.
As you may have noticed in the paper, there are numbers of structures, and I would like to talk about two in specific, arrays and linked lists. Arrays and linked lists are two common data structures, each with strengths and weakness. Arrays store elements in a continuous block of memory, allowing fast access in all one time. They are also space efficient since they only store the data itself. However, inserting ordering could be a problem because other elements may need to be chipped. In the other hand, we have the linked list. They excel at insertion and deleting, which can be done in all one time by simply adjusting pointers, but accessing to an element is slower since you must traverse the list from the beginning. They also require extra memory for storing pointers.
let's now describe a real-world example. Data structures are essential in many areas, such as databases, operating systems, networks, and artificial intelligence. For example, in databases, system V3s are widely used. Databases need to search through millions of rows quickly, so choosing the right data structure is key. A V3 balanced tree stores multiple values in each node, reducing the tree depth and making searches faster. Index and databases are often implemented as V3 separate from the main data, and which allows faster query.
If you ask me why it's important to choose the right data structure or how to do it, first of all, it's important because it's the key that affects the performance, the memory use, the maintainability, and scalability. A right choice ensures efficient operations, reduce resource waste, and makes code easier to maintain on a scale. So, how to do it? Well, here I have some tips. First, optimizing performance and efficiency. Second, meeting the problem-specific requirements. Third, ensuring maintainability and extensibility. And fourth, managing resource effectively. Knowing this, you can have a better idea on how to design a data structure.
Finally, what didn't I like about the paper we shared? I will read some of your opinions. So, Ingrid say the visual design feels flat and has high text density, which makes continuous reading difficult and can lead to visual fatigue. Okay, Brandon say it lacks graphic elements that support comprehension, such as diagrams, illustration, or visual highlights to organize the information. Finally, what didn't I like?
I'm reading your comments and I agree about the paper giving us a clear vision of the current revolution in data structure and the road ahead is amazing.